So today I'm talking about our recent work about a functional single-indexed model. This work is done with my collaborator, Fei, Jiang, and Yanyuan. The motivation for this work is it's about my theory about for the index. So when I started to get my job at SFU in 2007, I got the pretty good salary, and I'm thinking about investment. So how can I do the investment? So I read a book called Investment for Dummies. Okay, so it's a 500 pages book, and basically I read through the whole book. The conclusion is that you should invest the index because the index is easy and also cheap, and also they said they studied many mutual funds. Actually, no mutual fund are able to beat the index for long term, and the individual picked manage the mutual fund actually far more expensive than the index fund. So I decided to investment on the index fund. So if you think about the index fund, actually Greg also talked about SP 500 index. So we have all kind of index for the stock market. So the index is kind of a dimension reduction, right? So we have so many individual stocks, and they somehow kind of get some weighted average on the major stocks, individual stocks, and they give our a single index, right? So every day when we look at the news, we don't need to go to the individual stock. We just look at the news. It will give the Nasdaq index, and it's so easy to get this information, right? So therefore, this is kind of motivation for us. If can we come with some kind of more some elegant index model to do this dimension reduction. So let's first let me talk about another motivation examples. About air pollutants. Okay, so this is a study in 2000, and they have a very nice collection on many air pollutants, and for multiple U.S. cities for over 10 years. And so this data set is publicly available. So here I choose 4 air pollutants. So we can imagine that these air pollutants maybe have some effect on our health, right? So, but how can we identify the effect? That's a problem. And at the same time, we don't have time to look at the values for each individual pollutant every day. So ideally, if we can come with one index, so suppose I have some kind of cardiovascular disease, and I'm only focused on how these air pollutants every day will affect my health problem. So if we can develop some index specifically for some health income, it may be convenient, for the public to know whether they should pay attention to the weather at certain days. So this is the motivation. So basically, we choose a health outcome, which is in this case here is the annual death rate caused by cardiovascular disease. I call it CVD here. So basically, the idea is we want to come with some kind of weighted average of all these 4 air pollutants, so that it will be most related to the CVD disease. And so there's many studies to study the effect of air pollutions. Actually, for many studies, comprehensive studies, the conclusion is that they don't find the significant effect of air pollution on the health effect. So this is kind of against our intuition, but this is some very comprehensive statistical studies. They find no effect. So we actually also tried some simple functional linear regression models to study the time varying effect of these air pollutants on the CVD death rate, and we get the same conclusion. We find no individual air pollutants has a significant effect on the CVD death rate. Okay, so we want to push a little bit, and we are thinking, is that maybe the reason is that all these air pollutants maybe have some complicated chemistry things happening together, and maybe a combination of these air pollutants maybe will have a significant effect on the CVD death rate. So therefore, we decided to develop a single air pollution index that combined all the air pollutants together and to describe the severity of overall the air pollution levels to the CVD death rate. At the same time, so this index will be also a function of time, will change over time, and we also will look at how this time varying effect of this single air pollution index on the CVD death rate. So to achieve this goal, we propose a functional single index model to address these questions. Okay, so here is the introduction about this functional single index model. So basically here, suppose we have J air pollutants. So I have so these are all functional variable. So I have x1t to xjt. So we have J random functional variables. Okay. So what I want to do is I want to define a weighted average of this J functional covariance, and I come with an index called WT here. Okay. So so here the coefficient beta j to the functional covariance xjt represent the relative importance of the air pollutants to certain health outcomes. So if you think about here, we have J functional covariance, and after doing this linear combination, we only have one single index WT. So this is a dimension reduction, right? Yes. Okay, so this dimension reduction actually has a special term called a sufficient dimension reduction. The reason is that we assume that the response Y, so Y here is the annual CVD death rate in the subsequent year. So we assume that the distribution, the conditional distribution of Y on all these multiple functional covariance x of t will only depend on this xt through this integrated weighted index. Okay, so here f is a conditional PDF or PMF, and we don't know. So here this alpha t is a functional parameter. It captures the time varying effect of the air pollution index W of t on the Y. Here Y is the annual CVD death rate. Okay, so here our job now is to try to come up with this coefficient to this multiple air functional covariance, and also we want to come up with this functional parameter alpha of t. So we have two parameters, beta and alpha here. So, as we just said, Y is linked to W of t through this integral, and you can see here we make an assumption on the conditional distribution. That's the reason instead of the regular single index model, we typically make the assumption on the conditional mean. So that's the reason here we call this this is kind of the framework called a sufficient dimension reduction, because basically our integral term will give the sufficient statistics for the distribution of Y. So here, if alpha of t is known, then this model, functional single index model, will reduce to the central space estimation problems. And if the beta here is known, then the model will reduce to a functional dimension reduction problem. So here is a kind of, will give you a quick summary about the functional single index model. So basically here we come with one single air pollutants index that summarize the pollution's CVT levels. And so the regular sufficient dimension reduction framework is for the multivariate case. So we extend the sufficient dimension reduction framework to handle multiple functional covariates. And here we have a time varying coefficients alpha t capture the time varying effect of the air pollutants on the public health. And because here we assumed this conditional distribution f instead of look at the conditional mean, we have a pretty flexible relationship between this CVD death rate and overall pollution effect. By the way, if you can please feel free to stop me anytime if you have any questions. Okay, so this is our model. So now let's talk about our estimation method. So firstly, this model is not identifiable. So here we have two parameters. One is alpha of t, the other is this beta jazz. So here we can prove that if we assume that set the value of alpha t at time 0 equal to 1, and the last coefficients beta capital J equal to 1, then this model is identifiable. So here we have functional parameters alpha of t, and so we know that a convenient way to estimate this alpha of functional parameters is to write down this functional parameter as a linear combination of basic functions. So here bkt is a case B-spline basic functions. So if you so for the B-splines, if you're familiar with the B-splines, you may notice a unique feature for the B-splines is that the value of the B-spline basic functions. So only the first B-spline basic function at the starting point 0 will equal to 1. So all other basic functions at the starting point 0 is equal to 0. Therefore, to have alpha 0 equal to 1, it will be corresponding to set the first coefficient gamma 1 equal to 1. So with these two constraints, gamma 1 equal to 1 and beta j equal to 1, we kind of lose two parameters now, right? Okay, so now we have so beta we have j beta and we have k coefficients for the alpha of t. So now we will have j plus k minus 2 parameters in total. Okay, so now let's look at this integral more carefully after we plug in the basic function expansion for alpha of t. So here I show you some linear algebra. So we replace the w of t as a linear combination of this air pollutants, and alpha of t as a linear combination of these basic functions. And then we can do some linear algebra. We will write down this integral term as some quadratic form. So here we have this j by k matrix z. So this z has the entry as the integral of xjt to b times multiply bkt, because this xjt is the observed functional covariate, and bkt is a basic function we decided in advance. So basically here we can calculate this z by numerical integration pretty easily. So therefore here we assume the z is known. Okay, so this is about this integral. The key things or the most difficult work here is how to come with the estimation equations. So we have derived these efficient score functions, and so this is kind of give the form of the efficient score functions, and so with these efficient score functions, we can prove that this s by setting this efficient score function equal to 0, we will be able to estimate the parameters beta and alpha optimally, in the sense that they have the smallest asymptotic variance. And also, if we can able to correctly specify these unknown terms in the efficient score function, this estimator will be also consistent. But in reality, in these efficient scores, we have two terms we never know. One is this conditional expectation. The other is the conditional density function f. So this f2 prime is a second derivative of f with back to beta transpose z gamma. So we never know this, especially this conditional density function f dot. We never know this. Okay. So therefore, we are using some non-parametric estimation method to estimate these two unknown components. So the firstly, we were using the standard kernel smoothing to estimate this conditional expectation. So this is relatively easy. And then we were using the local linear estimator to estimate the conditional density function f here. And we can also obtain the derivative as well at the same time. So the problem is that when we do the local linear estimation for the density function f, it required a pretty heavily computation. Okay, so when the estimation variability is not of great concern, actually we can try to find some less optimal estimator to ease the computation burden. For example, we propose to just give a working model for the density function f, so like just any density function f, like normal density functions, so we can show that using this the working models, we can show that the estimation will still be consistent, and maybe have a larger variance. Okay, so but if f is the true density function, then this estimation is still efficient. So here basically we have two parameters. One is the beta, the weight to the air pollutants. The other is the gamma, the basic coefficients for the alpha of t. So here we have basically we are doing a profile estimation. So in the first step, we can either estimate the conditional density function non-parametrically, or we just give a density function subjectively. So after we know this f, then we can derive the efficient score function, and for any given beta, we can estimate gamma by solving this efficient score function equal to 0. So we denoted the estimator as gamma hat as a function of beta, because for any beta we'll get a gamma hat. So then we will estimate beta by solving the efficient score function for the beta functions. So now let's me show you the result on the applications. So basically, this is the applications I show you as a motivation example in the beginning. So here we have 4 air pollutants, and at 108 U.S. cities from 1987 to 2000, and we have the also have the annual death rate caused by the CVD disease. And so our objective is to study the effect of this 4 air proteins together on the death rate of death caused by the CVD disease, using the proposed functional single index model. So this is the pointwise mean trajectory of the 4 air proteins, and you can see here this NO2, CO, and SO2 has very similar trend, and it has exactly the opposite trend of the ozone. So they have a negative correlation. So here, this is when we do the functional linear models for each individual air proteins. So this x of t will for the individual functional air proteins. So here the y will be still will be the same response, CVD death rate. So the left one is when the functional covariance x of t is the air protein CO, and the right panel is the estimated eta of t when x of t is the air protein NO. So you can see this is the confidence interval, the dashed lines. So you can see the confidence interval always covered the zero lines. So which means that these air proteins have no effect on the CVD disease. But when we combine all these 4 air proteins together using our optimal weight, we come with this air pollution index. So then we can look at how this air pollution index W of t on the y. So now this is our estimated time varying effect of the air pollution index on the annual CVD death rate. So now and with this 90% confidence interval, so you can see here we have a very positive significant effect in the spring, summer, and the fall term. Okay, so there's no significant effect for the winter in the winter term, and the effect of this air pollution index to the death rate has the highest effect in the summer, in the middle of the year. Okay, so this x-axis is after scaled to 0 to 1. So the real time is from 0 to 365. So here is some examples. So we choose 3 major cities in the U.S.: Boston, New York, and Chicago. So you can see here, this here is to show the annual CVD death rate for these 3 cities, and this one is the air pollution index we come with. Okay, so you can see here. So the red dashed line is for the New York air pollution index. You can see here the New York has the highest value in terms of their air pollution index in the summer. So therefore, it has the highest CVD death rate in total annually. Boston, on the other hand, has the lowest value on the air pollution index, but the CVD death rate, therefore the CVD death rate is the lowest. Although the Boston has a higher values in the winter, but recall that this air pollution index had no significant effect in the winter. So the summer really matters for this CVD death rate. And we can also doing the prediction errors, and we find out using the single index models, it has the minimum prediction errors compared to the traditional functional single linear model, the functional additive models, and a conventional single index model. So we also doing a simulation study, and so this is it shows that our estimated alpha of t is very consistent to the true alpha of t, and also this is kind of compared to 3 methods. So the oracle method is to assume that the conditional density function is known, okay, and the efficient estimation is when we assume the f is estimated completely non-parametrically, the time-consuming one, and the locally is when we just giving a working model for the f without the estimated f. Okay, you can see all these 3 methods are able to estimate these 3 coefficients very consistently. And also we can look at their standard deviations. So for all these 3 methods, the average of the asymptotic standard deviation errors is consistent to the standard deviation from the simulation. And also we can see that for the local efficient estimator, it has a larger standard deviation estimation than the efficient estimator one. So we pay a price. And the same thing with the mean square error of the estimation. The local efficient estimator has a larger mean square error than the efficient estimator. But the confidence interval, 95 confidence interval, are all reach the nominal level, 95%. So here's the summary of my talk. So basically here, I presented you a functional single index model. So here, I assumed the conditional density function y depends on x of t only through this integral term. And we have this index w of t as a linear combination of the multiple functional covariates. This is called a sufficient dimension reduction for the functional case. And so hopefully this is kind of you give you the flavor that the index really is a very efficient dimension reduction tools and also help the interpretations of the result. Okay, I finished my talk. Thank you. Questions?
Yeah, there is actually already a functional single index model, right?
Yes.
And beta model. And that one
There's several.
There's not
Several. Yeah, several. That's right.
So
yeah.
My question is this: you could actually view this as a multivariate function.
Yeah, that was my question.
And then you didn't have to construct the index W because you can apply the single index to each component, right? And then you can apply the existing single index to each component.
Yes.
And then optimize those index in this sense. So my question is basically why you want to do the W. I'm kind of not clear about the motivation because you don't need it. You can do for each component
yes.
the functional single index model, and presumably doing that, we will be more flexible, right? Because then you can optimize the prediction for each component process.
Okay, I see.
So there are 4 single index functions. Same thing, you can use B-spline or eigenfunction basis, whatever you like. So, but you get 4 basis functions. You get 4 non-geometric functions.
Yes.
For each component. So you get a richer definition of the process somehow, I would assume.
Yes.
Because it would be that the data varies over time, but different components don't have the same influence at different times.
Yes. Yeah, this is a very good comment. I guess the idea here is that we want to do some dimension reduction. So suppose we have like a large number of functional variables. So whether we can kind of come with some kind of nice summary of the one-dimensional of the multiple functional covariates. Yeah, but definitely this your suggestion very. I mean, it's very good. Like so, probably your model will have a higher prediction power than mine. Probably, yes. Yeah.
I just want to ask something. I guess it's somewhat of a follow-up question to that question. Am I understanding it right? You're essentially using it as a power boosting technique. You're proposing you have a sufficient statistic of this form, and so you are simplifying your experiment.
Yes.
And you do that in the hope that you would have a more powerful technique. Is that?
Yeah. So the main idea is to get a dimension reduction. So we want to get just one index to summarize the multiple functional covariate.
So
yes.
my follow-up question is how would you let's say you do a model selection exercise, you compare this model versus the model that just suggested. How would you determine? How would you choose the criteria to determine which is the better?
Okay, this is a very good question. Yes, I guess it's really depend on your criterion, right? So if your criterion is to maximize the prediction error, maybe probably like Hans suggestion it will working better than mine. And on the other hand, if you want to get some simpler model, maybe yeah. So really it's up to your objective.
No, but
Yes.
that's the point. Like,
Yeah.
The point is how would you demonstrate that for the particular data set, the simpler model is
Sufficient enough, right? Yes. Yeah. This is kind of model selection problem. Yeah. This is I think it's still open, like how to do this. Yes.
Any other question?
So I'm just a little curious about your actually application. So usually death occurs quite late after exposure. So therefore, for instance, if I have exposure to pollutant, I probably will die a few years later. So
Yes. Yeah. Yes.
So if
Yeah.
you do a regression, in that sense, you are doing a 1 year's pollutant level versus the same year's death rate. Is that
The
right?
second year, the
Okay,
subsequent
so
year.
I'm just
Yeah.
wondering whether
You're right. Yeah, you're right. Like so definitely there's some lag effect unknown. So this is some open problem for sure.
Okay.
Like how to handle these lag problems. Yes.
And
Yeah.
also your confidence band you show is point-wise or simultaneous.
Point wise.
So
Yes.
that has a lot of multiple testing problem there. So if you really
That's
want to check whether it's actually covers zero or not, you want to maybe do some, for instance, bumper loading correction that makes things wider.
Yes.
So I was wondering whether that gives you
Yes. Yeah. So as far as I know, so in the functional data case, actually it's pretty hard to get the simultaneous confidence band somehow. Yes. Yeah. So but definitely that's a good question. Yes.
when in your identifiability assumption, you assume beta sub capital J is 1.
Yes.
So in practice, would you need to cycle through the because when you assume beta J is 1,
Yeah.
you assume in that
Air pollutants will have an effect, right? Yeah, positive effect. That's right. Yes, that's a very good question. So definitely, like you can basically theoretically you can put any beta j equal to 1. The model will be identifiable. So therefore, before you doing this, I guess you need to check which beforehand maybe individually which xj will have a positive effect on the y. Then you can set that one as equal to 1. Yes.
Or the whole scheme perhaps you have to test that data all, and then have a
Yes.
more selection receiver to pick on the best.
That's right. Yes, that's possible too. Yes.
Okay, thanks everyone. Thank you for being
Very quickly. You may talk to me for even longer if you want.
Yeah. So the thing that there's a big problem when you